see here. I will begin with a word of prayer. So, Heavenly Father, we thank you for this day again. I thank you for this class and just ask that you bless our work today. Help us to understand a little bit more about how to use Laplace transforms and help us to glorify you in what we do, Lord. In your name I pray, Lord Jesus. Amen. All right, so any questions before I dive back into it? So we've been starting to look at inverse Laplace transforms, and I've showed you a few of my methods. Other people do it a different way. They like set up a template and then fit the template. I try to teach you guys to be the template, which saves you like significant amount of time if you learn the method. But anyway, let's see here. So start with an example. Suppose y as a function of s is equal to, 3s plus 7 divided by s squared minus, let's say 5s plus 6s, all right? Here's the question, is to find the inverse Laplace transform of big Y, all right? So calculate the inverse Laplace transform of this thing right here, right?
Did you mean to put an S with that 6?
I did not, thank you. Wow. Yeah, we could do that. No, I didn't, but we could do that problem next. That's actually kind of the same problem, ironically enough. But no, I didn't mean to. Thank you. All right, so with all these problems, the first order of business is to identify the nature of the denominator. All right, like that's kind of what guides your solution method. So I'll start with that. Notice that s squared minus 5s plus 6 is equal to s minus 2 times s minus 3, right? So this does not fall in the category of what we did last class, right? And so the method here is called partial fractions. What we want to do is we want to set 3s plus 7 over s squared minus 5s plus 6. We're going to set it equal to some constant a divided by, say, s minus 2 plus some constant b over s minus 3. The technique of partial fractions says that there do exist a and b to make this equation reality. Now, the way you find a and b, you may remember from Calc 2, right? There's various techniques. If you come take the friendly, hardly approved to be seen in sight complex analysis course that we offer here every year, we teach a method in there which is a little bit different, maybe a little bit less, I don't know if it's really better, a little bit better. But this will do. So what we do is multiply both sides by the denominator, and that gives us 3s plus 7 is a times s minus 3 plus b times s minus 2, right? So multiply by denominator. Right? And then the easiest way to solve this equation is to plug in the roots, right? So like evaluate at s equals to 3. All right, so that's 3 times 3 plus 7 is equal to, I'll write it down, but I don't usually write it down, a times 0 plus b times 3 minus 2, right? And when we evaluate at s equals to 2, we get 3 times 2 plus 7 is equal to a times 2 minus 3 plus b times 0, right? So let's clean those up. What does this first one tell me? Yeah, b is equal to what? B is equal to 16? All right, cool. And the second one tells me what? A is equal to what? Yeah, negative 13, because there's a minus here. All right. Therefore, what do we have? Thus, y as a function of s is actually equal to minus 13 over s minus 2 plus 16 over s minus 3. And therefore, the inverse Laplace transform of y, right, at time t is equal to minus 13 times the inverse Laplace transform of 1 over s minus 2 plus 16 times the inverse Laplace transform of 1 over s minus 3 at time t. There I'm using I'm using the linearity of the inverse transform, right? Now you guys tell me, what is the inverse Laplace transform of, like, what is this equal to? What's that equal to? You guys tell me. We got, yeah, an e to the 2t and an e to the 3t. All right. So therefore, final answer, y of t is equal to minus 13 e to the 2t plus 16 e to the 3t. All right. I hope that makes sense. Now there is, I don't want to do it on this one, but I guess let me show you why not to do it on this one. Actually, this will be instructive. What's the other method I was using last time? Like so many robots, I always complete the square, you know? What happens if you go that path here? I'll start with 3s plus 7. Let me complete the square. Actually, I'm going to leave that blank. I'm going to complete the square downstairs. What I have there is s minus 5 over 2 quantity squared, right? And then I have to do what? I have to subtract 25 over 4 to be fair. Yeah? What's 6? 6 is 24 over 4, right? So if I subtract 25 over 4 from 24 over 4, I've got minus 1 over 4, right? Or minus a half squared, if you like. Right? And once I see that, I'm like, oh, well then I guess I should do 3 times s minus 5 halves, right? 3 minus, but that, if I do that, I have to do what? I have to add 15 over 2. And of course, I've still got the plus 7 there, yeah? But then, thinking about my life, I realized that I'm not content with this number just yet. So what I do is I take it and I multiply it by 2 and I write it times a half. At which point I can see that the inverse Laplace transform of big Y at time t is equal to, well, 3 times e to the 5 halves t hyperbolic cosh of, well, apparently t over 2. And then plus 29 e to the 5 over 2 hyperbolics times t sinh of t over 2. Which, of course, we could simplify. right? And if you look at that, we get 29, let's see here, like 29 plus 3 is 32 over 2 is what? 16. And then this times this gives me a 3t, e to the 3t. That's just from multiplying this times this, basically, right? And then, let's see here. The notice that I get a plus that and a, I think the terms that have I guess I should just multiply it out, right? So what do I have here? I also have a 3, okay, so 3 halves. What's 3 halves minus 29 halves is what? Minus 26 over 2, which is minus 13. And so those I've got 5 halves minus 1 half is 4 halves. 4 halves is 2, so e to the 2t. Ah, yeah, you know. Now, I don't recommend this method to you.
Really?
Right?
Did you just say don't complete the square?
I just said don't complete the square. No! What have I done? I've betrayed a friend. The worst. Oh man. This is worse than wearing a hat to class. Even worse. I've lost some subscribers over that. I've also gained a few though. It's kind of a mix. My son wanted me to wear it again today. Benjamin's like, don't forget your hat. Like, thanks, Benjamin. But yeah, I think you see why. Okay, so like, this is the same technique as I used last class for the ones where the denominator can't be factored with the reals, right? You can still actually do it, but it comes at the cost of this algebra, which is kind of formidable. This is way easier, right? You see that? Okay. Let's go on. So example 2. Let's try y of s equals 2, 3s plus 7 over s squared minus 5s plus 6s. Suppose I do that. What happens then? Let's find out, right? Again, find the inverse transform. So first order of business, clean up the denominator and factor it. In this case, we get what? We got s squared. That's actually plus s, right? Which is s times s plus 1. Great. So if I want to do the partial fractions decomposition here, I do a over s plus b over s plus 1. All right? So it really is just like example 1, as it turns out. And then multiply by the denominator, we get 3s plus 7 is equal to a times s plus 1 plus b times s. All right? And then let's see here. We'll look at s equal to 0, s equals to minus 1. See what that does for us. S equal to 0 gives me 7 is equal to a. S equal to minus 1 gives me minus 3 plus 7, which is 4, equals to minus b. So b is equal to 4. Lo and behold, we've got y of s is equal to apparently 7 over s there's a minus there, minus 4 over s plus 1, right? And I can write less than I wrote in the last example. Yeah, that's kind of my theme for my current work. So therefore, taking the inverse Laplace transform, we get y of t equals to 7 minus 4 e to the minus t. Okay? It's time for us to solve an equation. Let's try that on for size. Example 3, let's solve y prime prime plus 10y, oh, that's a bad choice, plus 12 y prime plus, oh, I don't know, 41 y equals to, let's put a 47 over here. Why not? And given y of 0 is equal to 1 and y prime of 0 is equal to 3. All right? So if you want to solve a differential equation by the method of Laplace transform, I mean, of course, we could solve this our previous way, right? And actually, that would actually be a better way here, truth be told. So I'm just illustrating the method. I'm not advocating this as a method to solve this problem on the final. On the final, you should use Laplace transforms for the problems which are most appropriate for Laplace transforms, namely the problems with discontinuous functions. As Laplace transforms are the only way to solve those. Whereas this we could use undetermined coefficients, you know. But anyway, it will illustrate the method, so let's do it. So we take the Laplace transform of the differential equation, right? So we've got like the Laplace transform of y prime prime plus 12 times the Laplace transform of y prime plus 41 times the Laplace transform of y is equal to the Laplace transform of 47, all right? I don't usually write down this step. I'm just writing it down this time so that the logic is hopefully clear. Now this gives you s squared times big Y, all right, minus s times something minus something else. You fill in the blank for me. Plus 12 times s times big Y minus something, you fill in the blank for me, plus 41 times big Y. The Laplace transform of 47 is simply 47 over s. So help me out. Let's fill in these blanks. Right? We worked this out the other day, but if you forgot, it's on the sheet in table 7.2, right? If you look at your handy dandy sheets, which I gave to you guys. Although I don't know, I need to like redo this whole thing because it's too fuzzy. But like the 1, 2, 3, 4th thing down is f prime prime. If you use your imagination, it says s squared Laplace transform of f minus s f of 0. So what is y of 0 here? Well, y of 0 is 1. And then y prime of 0 is a 3, right? And then this one is Laplace transform. So we do s Laplace transform of f minus f of 0. But here f is y, so f of 0 is 1. Right? So the things I just wrote in red, these are all initial conditions. And when we take the Laplace transform of a derivative, it folds the initial conditions into the calculation like this. Okay, so once we get that done, once you start working a few of these, and I know we haven't worked that many of them yet, right? This is maybe our second. You should start to notice a pattern. There's a pattern to be noticed here, which is that you'll always end up with like the characteristic equation for the problem. In this case, the characteristic equation is what? S squared plus 12s plus 41. Yeah, see that? That times big Y. The characteristic equation must appear as a cofactor to big Y when you gather all those terms together. This will happen. You can look for this. And then everything else is just kind of junk that is appearing because of initial conditions. And I'm going to move that to the other side. So this is equal to, S plus 3, don't forget to multiply by the 12, plus 12, plus 47 over S. All right. See, so like our next goal is to solve for big Y. Remember that flow chart I wrote at the start of all this? So I'm going back to that now. So we take the Laplace transform of the differential equation. We solve for big Y. Well, we're almost there. How do you solve for big Y? I guess I should probably clean this up slightly. This is what? S plus 15 plus 47 over S. Let's make that into a common denominator. This is what? S squared plus 15S plus 47 divided by S. That may seem kind of like a dumb step at this point, but it'll become apparent why we want to do it in like the next step. All right, so if I solve for big Y, what do I have? I have big Y is equal to S squared plus 15S plus 47 all divided by S times S squared plus 12S plus 41. Now what does it take to solve the differential equation? Do you remember the next step in the table? If you go back to that flowchart, if you look at it, the way we did, we took the Laplace transform of the differential equation, we solved for the big Y, and then the next step after that was to take the inverse transform. Right? Actually, there's another step before that, which is to rewrite the formula for Y into something pretty so that we can take the inverse transform. Because if you look at this formula right here, and then you look at your sheet, you'll realize that this is the Laplace transform of no function that you know. Right? Like, look at your sheet, look for it. It's not there. So we need to find a way to sort of manhandle this expression and force it to our, the pattern that we know how to understand, which are inverse Laplace transforms of exponential sines and cosines, products thereof, so forth. So you might guess what we're going to need to do here. We're going to need to, first of all, understand the denominator, right? So this is really S squared plus 15S plus 47 divided by S times what? Well, that's an S plus 6 squared, right? And if I do that, I have to subtract 36, right? Subtract 36 because I just added 36. What's 41 minus 36? What's that? 5. Oh man. Well, that was unfortunate. Can I fix that? I'd like that to not be 5 for the sake of the readability of this. Let me, if you guys don't mind, I'm going to make a slight modification here. I would like for it to, instead of be, I'd like for it to be, let's make it 9. That'll be nicer for the sake of our calculations. How can I make that be a 9? I need to change the 41 to a what? What's 36 plus 45? All right, so 45. There, that's a better example anyway, 45 and 47, like I planned. There we go. 45 and 47 in one problem. I don't know what possible significance that could have, but anyway, there we go, 45. 45. 45 is not equal to 47. Something to think about. Let's see here, 45. So that makes this plus 9, right? Yeah, yeah. Sorry, I was trying to do that in my head, and I failed. Oh well. Anyway, I like how it turned out. So, great. Now what do we do? Well, the answer is partial fractions. All right, so this is the thing I'm trying to teach you guys right now. We haven't covered this yet. We're covering it now. So to break this up, what I'm going to do is I'm going to rewrite this as, now watch this, I'm going to do a over s because that's nice. And then I'm going to do something a little bit different. So like the partial fractions you learned in Calculus 2 is a little bit different than what I'm about to do. What I'm about to do is to anticipate where we're going, which is the inverse transform. So what I do is I write b times s plus 6. You see, because that's what I'm interested in here. And then plus c times, well, 3 divided by s plus 3. And now if you didn't do that, it wouldn't be the end of the world. If you didn't do your setup just like I just did, it wouldn't be wrong. It just wouldn't be prudent, because you'd be making work for yourself in the step after this. See, because if I write that down, right, once I find the values for a, b, and c, I can take the inverse transform immediately from this expression, right? I can tell you the inverse transform of this is a plus b times e to the minus 6t cosine 3t plus c e to the minus 6t times the sine of 3t. All right? But then the question is, how do you find the a, b, and c? Well, multiply both sides by the denominator. What do we get? We get, oh, by the way, take a step back here for a second. Do you see why it was important that I made a common denominator in the previous step? Like here, what would happen if I didn't do that and I just went on my merry way? I'd divide by the characteristic equation, right? And then I'd have, you know, an s plus 15 over that, and I'd have a 47 over s times the characteristic equation, right? I'd still be left with the problem of needing to do partial fractions on the term with the cubic in the denominator, and I'd have the additional problem of figuring out how the s plus 15 over the characteristic equation comes together, you know? So why do two problems when you can just do one, you know? Now, there is a significance to this. This s plus 15 is somehow folding the initial conditions into it. So like there is a significance to this on its lonesome, but nah. All right, so let's do it. We got what? We got s squared plus 15s plus 47 is a times the characteristic equation of, you know, I'm going to write it as s plus 6 squared plus 9. And then plus, you know, b times s plus 6 plus, well, I'll write it as 3c this time, all times s. So again, as usual, multiply by denominator. All right. So, you know, there's some sort of low-hanging fruit here to pick, which is what? I mean, the easy part is s equal to 0, right? If we put s equal to 0 on the left-hand side, we get 47. And on the right-hand side, we get what? $45, right? 45a. This stuff's 0. Who cares about it? So therefore, a is apparently 47 divided by 45. Right? Now, there are various approaches for the other term. Let me show you one that is maybe new and kind of fun, which is to plug in the complex root. So if we plug in the complex root, what would the complex 0 of this be? it would be minus 6, and we could either go plus or minus, but I'm going to go plus 3i. Right? If I do that, well, it does come at a cost, doesn't it? Because then I've got to do, minus 6 plus 3i squared plus 15 times minus 6 plus 3i. There's actually something to think about on the left-hand side this time, plus 47. But the cool thing about that is it does make the term with a 0. Right? Because when we plug minus 6 plus 3i into this term right here, we get a times 0. And then you've got plus minus 6 plus 3i. That's from my s, this s here. Now notice that s plus 6 is what? S plus 6 is equal to 3i in this context. So this just becomes 3ib plus 3c. And then I just need to do some math here. So when I square this out, I get 36 minus 18i plus 9i squared minus, what's 6 times 15 is what? 90? Minus 90 plus 45i plus 47. That's equal to, on the other, over here, we get minus 18 IB minus 9. Well, I'll do plus 9 I squared B. I'll write all the details out here for a second. Minus 18C plus 9 IC. All right, let me try to simplify that. So I squared is minus 1, all right? And what you want to do is group all of the real terms together. All right, so we've got this 36, we got this 9i squared, 90, and 47. So that gives me 36 minus 9, which is 27. 27 plus 47 is 27 plus 47, 74. 74 less 90. Minus 16. I think the real part's minus 16 on the left-hand side. And how about the imaginary parts? Well, I got a 45i minus an 18, which is a 28? No. 27? Yeah, 27. So plus 27i. All right, we got that. And on the other side, we got what? What's the real part? So the real part on the other side is this guy and that guy, which is, you know, minus 9b minus 18c. And then we've got I times what? Times 9c minus 18b. All right, so that gives me minus 9b minus 18c equals to minus 16. And that's from the real part. From the imaginary part, I get 27. Oops, my bad. I get 9c minus 18b equal to 27. So I think as a practical matter, I'll multiply this one by 2 and get 18c minus 36b equals to 54. See, because then if I rewrite the other one right above it, minus 18c minus 9b equals to minus 16, then I can add these equations. And when I do, the c's, they be canceling, I get minus 45b is equal to 54 less 16, which is 38. Thank you. So therefore b is apparently minus 38 over 45. All right. At which point I can find C. Pick your equation. I'll pick the second equation. C is equal to 27 plus 18b all divided by 9. So that is 27 plus 18 times minus 38 over 45 divided by 9, which I'm going to get my calculator. So that works out to 59 over 45. All right. Now, is that the best way to do the algebra here? Probably not. There's probably a better way for this last part of it. Like, let me finish the problem before I say more about that, though. So what we found then is that y is equal to, in summary, 47 over 45 times s, right? That was my A. And then B was minus 38 over 45. And I'm going to write this as a separate term. S plus 6 over your s plus 6 squared plus 9. And then plus 59 over 45 times 3 over s plus 6 squared plus 9, right? Now, it's a simple matter to take the inverse Laplace transform and get y is equal to 47 over 45 minus 38 over 45 e to the minus 6t cosine 3t plus 59 over 45 e to the minus 6t sine of 3t. Now, okay, so there it is. But so you see that the kind of inverse Laplace transform technique we're going to need for a quadratic equation, it's going to not just be a quadratic denominator, right? It's going to end up being possibly a cubic, possibly a quartic. I mean, it kind of depends on the forcing function, like what we're going to be up against. Okay, so this last bit where I did complex, can you guys tell me another way I could have gone here? So like, let's go back to this equation. Let's call this equation star. So going back to star, what else could we have done differently, perhaps? How about this? Well, s equal to 0 annoyingly is already taken up. Usually s equals to 0 is a good option, right? But it just so happened that it was already used up here. So if s equals to 0 is already used up, I look at the expression and I ask myself the question, what makes this relatively simple? Well, I've got an s plus 6 here. So s equals to minus 6 is a good choice to get a nice equation. You know, s equal to minus 6 is going to be nice. That's going to give me minus 6 squared, right? Plus 15 times minus 6 plus 47 is equal to what? Well, it's equal to a times 9, 9a, right? It's equal to 9a, and then plus what? That's 0, so we get 3c times s, which is minus 18c. So you see, that was actually pretty nice. I could solve that for c directly. C is equal to what? You know, whatever this is, which is, you know, minus 90 plus 47 is 43. 43 plus 36 is what? $79? Did I got 79 there? I don't know. So anyway, let me not finish this because I don't want to do all the algebra over again. The point is you can solve this for C because we know A. We already know A from the easier step, right? And then once you know that, there are various tricks you could do, but I would just try putting in something really simple like, s equals to 1 is nice, because then you've got 1 plus 15 plus 47 is, what's that? 49 plus 9 is 58, so 58A. Plus 7B plus 3C. And the thing is, at this point in the calculation, you already know C from the previous step. You already know A from the step we did over there. So then you can solve for B, right? This is probably a better way than the complex way for you guys, right? Because you're not that comfortable with the complex arithmetic, most of you. And there's a lot of, I'm just saying, there are other problems where the complex arithmetic makes things like very easy. This is not one of them. It's not really that helpful. So.
Can you also compare coefficients?
Yes, you can also compare coefficients. Very good. And that's not a bad way either. Comparing coefficients, nice idea. Of course, the constant coefficients we already got, right? But thank you for reminding me about that. Compare coefficients. That is a good idea. If we did that, we'd have like for s squared, right? We'd have 1 here. How many? We got a. This gives us an s squared, so we get plus a. And I also get an s squared from here, so I get plus b. Ooh, that's real nice. I think that's better. Thank you. This one, 15. So I use an amalgam of all these techniques, depending on the problem. So this one's a little bit trickier. To figure out the coefficient of s, I need to FOIL that out. That gives me a 12a in there. So I've got a 12a. And there's also plus a 3c here. Well, plus 6b, I should say. Plus 6b. Plus 3c. And then the constant, we've already seen that. This is the s equals 0 equation. That's going to give us 47 is equal to, 45a, yeah. So yeah, you could also solve those 3 equations. It doesn't, you can use whatever technique you want. I just need you to be able to find the partial fractions decomposition for these kinds of problems. And the only real way to get good at these is to practice, right? Probably need to do at least 4 or 5 of these before you're really even starting to get comfortable. At least I think. For me, it was that case. So I don't know, but there are, of course, many more cases to talk about with the partial fractions decomposition. Let's deal with a couple of those in the time we have, because I can talk about setup, talk about the setup without actually doing the algebra, So let's do that a bit. So some partial fractions advice. If I had something like 3s plus 7 over s to the 4th minus 81, if I had something like 17s plus 1 over, I don't know, s squared plus 3s plus 2 quantity squared times say s plus 1, we could talk about these. That's probably all we got time for. So the top one, we factor the denominator, right? You've got s squared plus 9 times s minus 3 times s plus 3. That's what you got when you factor that out. That's what you got. This one down here, we've got 17s. The numerator is irrelevant, by the way. As long as it's got a lower degree, that's all we really care. So this is s plus 1 times s plus 2 quantity squared times s plus 1, which is, we got a total of s plus 1 cubed here times s plus 2 squared. All right. So the setup for the top one, I do like as plus b over s squared plus 9, and then plus c over s minus 3 plus d over s plus 3. That would be my partial fractions set up there. If I work that out, then I can take the inverse Laplace transform of this function, no problem, right? This one here, the setup is this. You do a over s plus 1 cubed plus b over s plus 1 squared plus c over s plus 1 plus d over s plus 2 squared plus e over s plus 2. All of these terms are readily inverse transformable. So these are wise partial fractions and decompositions. In fact, they're the only ones available to you, up to like rewriting expressions in a non-productive way. As a general rule of order, let's just notice the pattern here, right? It's important to notice patterns. This has degree what? What's the degree here? Degree 4. This is degree 5. How many coefficients do I need? 4 coefficients, right? How many here? 5 coefficients. This was not an accident. The proper partial fractions decomposition, the number of undetermined, they're not really undetermined, the number of parameters to be determined in the partial fractions algebra should match the degree of the denominator which you're finding the partial fractions decomposition for. So anyway, there's that. I think probably next class I'm going to move on to the discontinuous case, and we'll start looking at those. Because as we go on to that, we'll still face all the algebra we're currently doing, and we'll get better at it. So thanks, guys.